This lecture covers non-parametric tests for group comparisons. The first question you might ask is, why use a non-parametric test? We've said several times in the course that parametric tests are more robust and should be used whenever possible. However, parametric tests have to meet several assumptions that cannot always be satisfied in real life. Sometimes data isn't normal, and so non-parametric tests offer another way to test hypotheses when we can't use the parametric test that we'd like. If this is your typical study subject, you should probably plan to use a non-parametric test. Obviously, this would not be considered normal. Why not always use non-parametric tests? After all, testing assumptions is a bit of a drag. When data are normally distributed, parametric tests are more powerful. They're less likely to be subject to a type 2 error. So whenever you can, use a parametric statistic. When you can't, use a good non-parametric test because they're a good backup plan. Non-parametric tests, also called distribution-free tests or non-distribution tests, are used when the assumptions of normal distribution and homogeneity of variance are not met. This is a typical occurrence in studies of pathological conditions, small clinical samples, and the use of convenience samples. In clinical studies, it's not always ethical or possible to randomize subjects to treatment and control groups. Convenience samples include all possible subjects for treatment. Data are measured on a nominal or ordinal scale. Non-parametric tests allow for the measuring of the frequency, number, and percent of data. One more thing. Use non-parametric tests alongside parametric tests when your assumptions are close to not being met. If the non-parametrics match the parametric test, you can feel confident about using the parametric results. Now, even though non-parametric tests are considered distribution-free, we still like to meet some obligations and assumptions. Whenever possible, some type of randomization should be used, but we realize this is not always possible. We wouldn't want to randomize patients on a floor to treatment and non-treatment groups. That would be unethical. Data should be at least ordinal, and sometimes we can take data that are not ordinal, so they're continuous data, and we can make them ordinal so that we can make comparisons when their distributions don't meet the normal curve, and they're not they don't have equal variances between compared groups. The sample size of a non-parametric test, whenever possible, needs to be much larger in order to be on par with parametric tests. A 65 to 95% power efficiency is needed. Now, what that means is, for every 6 subjects we have in a parametric test, we would need 10 for a non-parametric test. Again, we use non-parametric tests sometimes because we have small sample sizes, so this isn't always true. But if we're planning ahead and we can get the large numbers, go for it. The next slide shows you a table of backup non-parametric tests that can be used with the assumptions of the parametric tests are not met. So the first one you see here is the independent t-test. If we don't have groups that are equal to 30, where both of them are equal to 30, or we do the homogeneity of variance and they're unequal, then we can slip over and use the Mann-Whitney U. There's also the Wilcoxon rank sum test. The Mann-Whitney U is one of the more powerful non-parametric tests, and we'll actually look at how to calculate that by hand. The Wilcoxon sign rank is useful for paired t-tests, and we talked about the fact that with the one-way ANOVA, if we had a small sample size and we checked the homogeneity of variance, the Levines, and we found that it was significant, we could use the Kruskal-Wallis test. We didn't cover repeated measures ANOVA in this class, but if you cover it in a later course and you don't meet the assumptions required for that one, Friedman's ANOVA is available. So as we said before, non-parametric tests in general require that data be ranked. Here's a how-to guide on ranking data. Rank scores from the smallest to the largest with a rank of 1 going to the smallest score. Use the lowest rank for the largest negative value if a data set does contain negative values. The highest rank will always be equal to the number in the sample size. When two or more scores have the same value, for example they're tied, they're given the same rank average. And I also collected two samples of this, one that is with and one without tied scores, and this is from a Portney-Watkins text. So you see here in sample A that we have 8 subjects, and we ranked them according to, from least to greatest. So our least score was a -3, and our greatest score was a 16. Over here we have 3 occurrences of the number 11, and so those are averaged together and given the same rank, as well as we see here with number 3. So this is how you rank scores for just about every one of these non-parametric tests that you would enter into SPSS, or do the hand calculations. Let's do an example with the Mann-Whitney U. Again, I'm getting this example from a different text, but this is used when we have violated the assumptions of the independent samples t-test. A researcher wants to know which position is most relaxing. Relaxation is measured by E&B biofeedback from the frontalis muscle. 11 subjects are randomized to one of 2 positions for a pre-test post-test design. We write our research and null hypothesis. There will be no difference between mean ranks of relaxation based on position, or there will be a difference in mean ranks of relaxation based on position. We set our level of measurement, and then we rank our subjects. So in the first group we have 5 subjects in 1, and we see the rank, or the actual numbers, and then how they're ranked, and then we look at the sitting position numbers and we rank those. We combine all our observations and rank the scores in order of increasing size. So this is all of the scores have been ranked. We compute the Mann-Whitney U according to this equation. So if we compared the Mann-Whitney U from group 1, Mann-Whitney U from group 2, we always select the smaller value for Mann-Whitney U. In this case, it's 3. We compare this number to the critical value needed to reject the null on the Mann-Whitney U distribution table. This table is not in your book. I have it on the next slide. One thing important to remember about this particular table: this table requires that the critical value needed to reject the null should be greater than the obtained value. This is the opposite of all the parametric tests that we've done to date in this class. So remember, we go with the lowest number of the 2 groups that are being compared, and we look in the table to find the critical value, and we reject the null when the critical value is greater than our obtained value. So here is the distribution table for the Mann-Whitney U, where you have N1 and N2 sort of correlate with those degrees freedom, and we see that with a group with 5 in one and 6 in the other, our critical value is 3. That happens to be the same thing. Well, a rule on using this table: if it's the same or greater, we reject the null. So in our example, using the smaller value for U, we compare it to the critical value. Since our value is 3 and the critical value is 3, we reject the null. Again, just the opposite of other distribution chart procedures where a value greater than the critical value was needed to reject the null. One more thing, for larger samples, that means numbers greater than 25, we can't use this distribution table. We would convert the value of U to a z-score and compare it to the normal distribution, which is what we did earlier in this course when we learned how to compute z-scores. It would be easier to use SPSS with a sample size of greater than 25 to convert all of the individual samples to z-scores. Other non-parametric tests are quite similar to the example that I provided for the Mann-Whitney U. We rank the data, compute the statistic, use the lower value to compare a distribution chart critical value needed to reject the null. Most of the calculations for non-parametric tests can be conducted with a calculator and a pencil, especially when sample sizes are small. However, remember we said larger sample sizes are needed to make non-parametric tests of equal robustness to parametric tests. With larger sample sizes, SPSS would be preferable to hand calculations. We're less likely to make mistakes, and output files are very easy to decipher. Research questions in clinical and behavioral science often involve categorical variables such as Likert scales, yes-no answers, age groups, education level, political affiliation, even things like diagnoses. For example, we might want to know the proportion of patients with a different type of stroke who are able to be discharged home versus those who have to go to a nursing home, those who were not independent with activities of daily living after a 21-day stay in the rehab. We might want to know the proportion of ASN prepared or BSN prepared nurses who progress to advanced degrees. These types of investigations are best tested by determining if there's a difference between the proportions observed with a set of categories and the proportions that would be expected by chance alone. These tests use the Chi-square statistic. And here is the equation for Chi-square. Chi-square is the sum of observed minus expected squared divided by the expected values. There are some assumptions of the Chi-square test. Obviously, we want to use nominal level data. This is where we would collect frequency like number and percent, so it would be non-continuous. A minimum of 5 observations in each category must be compared. If we don't have 5, there is another test we can run called Fisher's exact. The groups have to be mutually exclusive. In other words, no subject can be placed into more than one category. And the categories being compared must have a reasonable theoretical basis. Let's say the discharge planning nurse wants to know if there's a difference in the proportion of types of stroke patients who can return home to independent living after 21 days of rehab. This will call for a one-sample contingency table. So we have 3 different types of stroke: ischemic, hemorrhagic, and the TIA. We have some data that we've collected. We note that of 126 patients observed over the course of several months, 36 patients with ischemic stroke returned home, 30 with hemorrhagic stroke, and 66 with TIA. And so our research hypothesis is there's a difference in the frequency or proportion of occurrences in each of these categories, and our null would state the opposite. Our level of risk is 0.05, and we select the Chi-square because this is a test of frequencies or proportions of mutually exclusive categories. It's helpful to make a Chi-square table. We are looking at one outcome and 3 categories. Now, the first thing we need to do is compute our expected. This is simply an average. We have 126 observations. We have 3 categories. 126 divided by 3 would be 42. And so if our null is true, then we would expect there to be an equal number of observations in our little study here. So expected is 42. Remember the equation. We're going to subtract one from the other. And so the difference between 42 and 36 is 6, 12 for hemorrhagic, and 24 for TIA. We now square this difference, and then we divide by expected. And so we see that 0.85 for ischemic, 3.42 for hemorrhagic, and 13.71 for TIA. We simply add these three numbers together to get our chi-square, and that's equal to 17.98. Degrees freedom is always equal to number of categories minus 1. So our DF is 2. If we look on table B5, page 364 of your book, it indicates that the critical value to reject the null is 5.99. There is a difference in the proportion of patients who are discharged to independent living based on the type of stroke, and you see the correct way to report the chi-square. Let's now do an example of a two-sample contingency table. Let's say that we want to know if there is a difference in the observed and expected occurrences among categories of RNs who earn advanced degrees. We write our research and null hypothesis to reflect that research question, and we set our level of significance at 0.05, and then we write a contingency table. We can simply do yes or no here, and then we have two categories: the ASN prepared nurses who go on to get advanced degrees, and the BSN nurses that we observe, say maybe in a particular graduating class. So 3 of the ASN do, 16 do not, 8 of the BSN do, and 13 do not. Again, we do the same as we did before. A little bit of a calculation here. There is our chi-square formula for a two contingency table where we consider all possible interactions. So if you want to fill in the numbers, it's not difficult to do. Again, most of these non-parametric tests can be done with a calculator and a pencil. And so when we finish, we see that our chi-square is 2.49. There's always a DF of 1 with a 2 by 2 table. We see by comparing at the back of the book a critical value at 0.05 with 1 degrees freedom is 3.84. There's no difference in the observed and expected occurrences among categories of RNs who earned advanced degrees. And we write it as chi-square is 2.49 with a p greater than 0.05. We can also use SPSS to conduct non-parametric tests. They're found under the Analyze Non-Parametric Test button. However, chi-square is found under crosstabs. So you can see it in two places. When you run your mouse over non-parametric test option, you'll see the dialog box on the right, or something pretty close to it, since this one is from SPSS version 18. So chi-square is the same as the one under crosstabs, but in this class you're going to want to use the one that's under crosstabs because it gives you more features. And then you see these other different kinds of tests that can be done. We won't be using these for your procedures in this class. So here's a question that's been answered by chi-square. Is there a difference in people born by month of the year over a 12-month period? This is a large data sample with 1,487, and we see that even though it computes a mean, this doesn't really mean anything to us because these are categorical data, so pay no attention to that. We have the observed numbers born in each month, and we average it and get the expected number. And chi-square will, SPSS will compute the chi-square. And we see that there is a difference in people born by month in a 12-month period. Chi-square with degrees freedom 11 is equal to 24.249. and our p-value is 0.12. Excuse me, 0.012. I mistyped that. So pay attention to this box here. There was a significant difference. And if we look at the two-sample or two-sample contingency table, is there a difference in percentage of males and females attending a sporting event in the last year? So we take the same sample set apparently in this study, and we're going to look at gender and yes/no categories of attending a sporting event. So here's for the male. We have 384 males who attended and 254 who did not, for a total of 638 males in the sample. Notice that 60.2% of males attended a sporting event in the last year. Now in the overall, that's 42.8 of the sample attending sports events were men. Let's look at the females. We see that 47.8% of the females said that they attended. If you look at the total sample, it says that 57.2 of the total sample of 1480 something were attending. So it looks like more women attended than men, but you must look at the sample size. They're different. Men was 60.2 and women 47.8. The overall difference is due to the fact that there were more women than men in the sample. So when we look at the Pearson Chi-square, we see that it's equal to 22.376, and that is significant. And so we conclude that there is a difference based on gender in number of people attending a sporting event. And since we know how to interpret that previous table, we would presume that men are more likely to attend than women. In addition to the chi-square, we see a continuity correction and a likelihood ratio. So if we had a very small sample, we could look at that as sort of a backup plan to even our chi-square. And Fisher's exact, as I told you before, is used when samples are really small or we have violated even the assumptions for a chi-square. So the correct way to write this, we conclude there is a significant difference in the percentage of males and females and attendance at a sporting event in the past year. Percent-wise, significantly more men attended a sporting event than women.